This week's multiple choice Monday is about giant covalent structures, and it's not really a big one for explanation. I included this question because of the number of students who tend to neglect silicon dioxide as an example of a giant covalent. So one thing we should know is that our aluminium and manganese compounds are classic examples of ionic structures, because we have metals and non-metals going together. Now our phosphorus oxide down here, our P4O10, is definitely going to be covalent in structure. So how do we know that that is not giant covalent? Well, there are a couple of reasons and a couple of ways that we can go through and sort of work out that silicon dioxide is the correct answer, other than learning it. So one thing you should know is that really there's only three common examples of giant covalent, and that is graphite, diamond, and silicon dioxide, which is also known as just silica. It's what we find in sand and quartz and other minerals. So one thing we should have in common is that all of these contain group 4 elements. So group 4 means that they're forming 4 covalent bonds, tetrahedral structure. Now I know that graphite doesn't have this structure, but what diamond and silicon dioxide have in common is that they can make a 3D arrangement of covalent bonds. So they can just basically keep bonding in all directions, which is how we get to this giant structure. So silicon dioxide has a structure just like diamond, in that each silicon has this tetrahedral bond arrangement, and each silicon is bonded to an oxygen, and then each of those oxygens is then bonded to another silicon, and so on, and it carries on throughout the structure. And I'm no good at drawing it, and you don't need to know how to draw it. So that's one thing. Think about group 4. Group 4 form these giant structures because they can sort of keep making bonds. The minute you get to group 6 and 7, then we're talking about making double bonds or single bonds with each other. There's not really an opportunity to make a giant structure on your own. So what about phosphorus? How do I know that it isn't sort of like in this giant structure? Well, one is you're going to learn these are your examples of giant covalent, but the other one is actually in the formula. So that P4O10, that's not the simplest possible formula. That is a molecular formula. It's not an empirical formula. So if I simplified it to the empirical, it would be P2O5. But if it was a giant compound, we would simplify it to its empirical formula. All giant structures are represented by the simplest possible ratio of the atoms that are present in that structure. So if I see something that's not the simplest possible ratio, that is definitely not a giant structure. It is a molecule, because I'm telling you exactly how many atoms there are present in that molecule. So, revision materials on my website. If you want to sign up to my A-level masterclasses, there's no more spaces in the AS level, which is a shame because we're doing bonding and structure this week. But there is the option to sign up for recordings access, and if you don't want to pay for that, there's also lots of free revision materials, ckchemistry.co.uk, and if you go to that website you can also sign up to my free chemistry revision club, Cation Club, where you get weekly emails with different ideas for revision, different videos and things to help you along your way. And of course, if you subscribe to my YouTube channel, then you'll be notified of new videos every week as well.